All right, folks, this is Dr. Faruqi again, and we are talking about the survival analysis. And in my last presentation, we talked about the parametric method for the survival analysis. Today, we are going to talk about the non-parametric survival estimation method, and today's topic is very important. All right, so basically, in a non-parametric estimation method, a non-parametric estimator is developed to study the survival function, the hazard function, the cumulative hazard function, the hazard ratio. And normally there are three non-parametric estimation method, and the most important is Kaplan-Meier. So Kaplan and Meyer in 1958 developed a non-parametric method to study the survival function for a right censored data. Keep in mind, for a right censored data. So Kaplan-Meier is used for the right censored data. We will see this will be the one of the limitation of a Kaplan-Meier estimation method, um, and is based on the order in which the events and censored data occur. Furthermore, we can study a single group, we can compare two groups, we can compare more than two groups with a Kaplan-Meier estimation method. So let's see how we can define Kaplan-Meier estimation method. If you have a non-censored data, suppose this is the time t1, t2, is your observed event time. What you're going to do is arrange this time, ordered this time like this. Uh, Start time, second, third, and so on. Ordered this time from smaller to higher. Okay, and the formula is very simple, just like a probability. Favorable cases, right? Surviving or alive past time t divided by the all possible time uh, or t naught. Cases at t naught, or you can just say your sample size, and this will just denote the formula. Let's take an example to see this one. Suppose in a clinical study, 30 of the 100 patient died at the end of the first year, then 20 of the left patient died at the end of the second year. What is the survival probability uh, that the patient will live more than 1 year? What is the probability for um, more than 2 years, right? So very simple. So at first time, how many total? 30. How many died? Three. Just subtract them and divide by the total. You will get 70% probability of survival. And after 2 years, 20 more also died. So subtract from the total and you will get the 50% survival rate. And this is very simple, just like a probability. But if you have a sensor data, again, uh, you have a time, order the data. Now the formula is this one. This is the pi is the product function. T time, arrange time less than equal to t, 1 minus dj over nj, right? What is dj, what is nj? We'll see that. So t subscript j in bracket, this is your order time, right? Nj, number of subject known to survived up to the time tj, right? dj is the number of events. Events, could be death, could be marriage, could be your first job after graduation, relapse, whatever you are interested in, right? And note that this idea of the formula of this is based upon the conditional probability. We will see this later. What are the properties of Kaplan-Meier? Kaplan-Meier is a right continuous step function as shown in the graph. See, it's a step function, right? And what is this? It jump or discontinuous at observed event time only as shown in the graph. See, at this time, when some event observed, it jump like this and move like that. At this, it jump like that, right? And then start moving. Once event occurred, it's jump and start moving. When event occurred, it jump and start moving, right? This is the property, you can say, Kaplan-Meier. When there is no censoring in your data, so this is just an empirical curve, right? Very important property for the large sample size. uh, your Kaplan-Meier is asymptotically approximately normally distributed, right? And this is again a very important property. Uh, if at the end of the study, right, if your time is maximum and you don't have a subject left at risk, that is your n at the maximum time is 0, with no event like dl is equal to 0, then the Kaplan-Meier estimate s of t is undefined. How? Look at that. If this is 0, this is 0. 0 over 0 undefined. 1 minus anything undefined, undefined. So this will become undefined, right? If at the maximum time no death, no person left at risk, then this function will be undefined. Again, at time maximum, no event left, number of no events is same number of no subject left. Like if this is equal to this, then Kaplan-Meier estimation function will be 0. How? If you if this and this same, the ratio will be 1. So 1 minus 1, 0. So survival function will be 0. All right, explanation, right? Uh, let's explain this, how we can get this formula by conditional probability, right? This is the formula for the conditional for the Kaplan-Meier, or we can say product limit estimate. Both name can be used we can see in the literature, right? So now try to understand this. So if you want to survive up to time t, you have to survive before that, like t1. Then you have to survive t2 up to t3, t4, t5. Then you will reach up to time t, right? So it means to survive up to the time t, you will survive at first time, then second, and so on. Now let us see like this. If there and you because uh, you have survived from this to this, it means the death between these two, there's no death, which is 0, right? And what's the probability of death between this and this? Could be di over ni. What is the conditional probability of the death? 1 minus this, right? And if you multiply these probabilities, you will get this formula, right? This is, you can say, tricky sometimes to understand, but it's not a big deal. I will give you an example, and I think we will be more uh, understandable concept we can have. Let's take an example application in real life, right? Uh, I took these examples. We already have this in previous example. So I have 6 subject. This is the time, right, in weeks, and this is the censored data. Like after 30 week, no death. Like sorry, no censor. If data is not censored, mean there is an event. Data is censored mean yes, mean there is no event, no event, no event, no event. Yes, right. Let us define our variable. Capital T is your random variable. Tj is your observed time. This is your observed time, right? I put plus beside that, which tells me that this is a censored observation, right? Now arrange the time, ordered time, and define your deaths. What is in our example, our event of interest is death. It could be, I said, marriage relapse or whatever you can define. And nj is the number of subject that have survived to time tj. This is the formula, right? And now we arrange the time, right, where plus sign tells you the censored observation. So from smallest to highest, right? So after 17 weeks we have an event, so we'll see the probability will change. These two censored, no event. After 30 weeks we have an event, and after that we don't have an event. So let's calculate the probability by hand. So at 17 week, this will be the formula. So we have one death here. How many total we have? 6. So put the numbers here and you will get 83% uh, survival rate at 17 uh, up to 17 weeks, right? Then at 20, when time is 20, like after 20 weeks, so this is a censored observation, so there is no event, no death. So how many left at this? So count this, there are 5. Is there a death here? Is there an event here? No. So this will be 0. 0 something 0. So and since we also want since time is less than equal to 20, so 17 is also included in this, right? So this event is already occurred, so that's a conditional probability. You have to multiply this with this. So that is your uh, survival rate after 20 weeks. When time is 30, after 30 weeks, this will be the formula. Now how many deaths? 1. How many total left? Here you left 3. So plug the number here, and you are 30. You start from the origin up till 30. So you have to multiply. This is already occurred, so you have to multiply this with your probability. This is basically product. This tells you. Then at 32, so this is censored value, no depth, no event. So this will be 0. So you have to multiply this with the previous probability, and so on. Again at this, you can calculate same probability, right? It's very easy, right? But don't worry, computer will do for you. All right, we define some, we already said that for the large sample, this is asymptotically normally distributed. So we define a estimate the variance of this, right? This is a Greenwood formula. I do. There is a proof. Definitely, there is a proof of this formula, but right now we are not interested in that. We just define these variance, and we know uh, if we have a variance, we have an estimate, then we can find a formula like a z, which is your estimate estimator minus estimate over standard error of the estimate. And for the large sample, this is normally distributed with zero mean and unit variance. And if you want to calculate the 95% confidence interval population survival function, you can calculate this. But the problem of this formula is you can get a value greater than 0 or less than 0. So try yourself, and but theoretically this is like that. So to fix that, we define a function L of t, which is double log minus of this, and you can construct the 95% confidence interval for this one. Again, all these are mathematically proved. So if you use this one and go back to your original data, so that will fix this problem, right? You will get the proper range of your confidence interval. All right. So now let's use the computer. So same data, you can use SAS, SPSS, R, or whatever. So this is your case summary process, case process summary, processing summary. You have 6 total. How many events? 2, 33%. How many censored? 4, 66%. And this is your table. So you can use the table. This is your output from SPSS, R, or SAS, whatever. So arrange the time. These are your subject at the corresponding time. These are your time in weeks. These are the event. That's the probability I already calculated. So when you have a censored value, you don't have any probability survival. So because basically this is same as this is same as this. So initially, basically we calculate the probability when the event will occur, right? So these are some more information. This is the standard error you will calculate. Now let's make a graph. That's good. So we plot the graph, and we can see it's a step function, and it will give us the survival probabilities. And what this graph tells me, so this is the horizontal line from when time is 0 up to time 17, right? So that represents the duration of your uh, time, survival duration of the particular interval. So it will terminate or discontinue when event happens. When the time, when the after 17 week, the event will have sorry, happen and it's jump, and then start up to at here event happen and it's jump. So these values, small dashes, will give you the censored observation. Vertical line represents the cumulative change. So this is a cumulative change. How much change do you have? And if you want to calculate, just subtract from 1, you will get this. Vertical line represents the censored value. Okay, and this was for one group data, one group. And if you want to compare 2 group, so let's take an example, right? I have an example. I want to compare a control group with a treatment group, and the event of interest is a remission from leukemia patients, right? One for yes, zero we don't know. So this is the data. We have 21 patient treatment time. This is the event. Control time, this is the event. So at 6 weeks there is one event. Same. So basically at 6 week we have three event. 7 week we have one event. 10th week we have one event, and so on. Ninth no event, no, so on. And here we have an event. So let's use SAS SPSS R, and this will give you, see, total 21, number of events 21, percentages censored 0, and so on. This is overall. And once I will get more output. Here is the time arranged, the SU status. These are the probabilities, survival probabilities, standard error, and these are some more information if you are interested. That's for the treatment group. And if you plot this, oh sorry, these are the, the means and standard error with the confidence interval, and the median and the standard error of the with the 95% confidence interval. Control group, you have mean this one with this standard error and 95% confidence interval. This is your median. Remember, we will use median, not the mean, because this is a skewed data. So this will not a good representative. This is your representative data. Median will be more representative as compared to this. So this is the overall median and the standard error in 95% confidence interval. So if you want to compare, you have to use some kind of test. Here we use log rank test. We will talk about this one. Just keep it here as it is. So let's plot the graph. Here it is. See, this is your, I think, treatment group, and this is your control group. And you can see uh, this not much steep, but this is very steep. This is shallow, and this is steep. And remember, if you go to the, the water park and you want to take the slide, and if it's steep, you will scared, right? You think there's a risk of injury. So that's why if there is more steep, there's a more risk, right? More hazard. So it means your control group is most hazard as compared to the treatment group. So treatment group is good, right? So it means treatment works as compared to this. So this one more steep, this is shallow, right? Shallow mean less risk, less hazard. Steep mean more risk, right? So you can see just a graph and you can tell what's going on here. Anyhow, so what is this? So that's basically the explanation that we did in by hand. Like when time was 6 week, right? 3 subject failed or died. What is the remission rate? Again, 1 minus, this is Kaplan-Meier formula, 1 minus di over ni, right? And this is your probability of survival. This is your failure rate, and 18 subject left. So on. When time was 7 week, one more subject died. Again, this is your formula, multiply the previous probability, and so on. You can calculate this by yourself. I explained this. If you wanna see this, you can get this from here. Anyhow, same thing for your other group. Now, if we can study one group, as I said, we can compare two groups, three groups, four groups, so on. If you want to compare two, three groups, you have to use a log ranked test formula, right? So you can compare two distribution, survival time, or the hazard. But right now we want to compare the distribution of survival time is same in two group. H1 alternative hypothesis, there is a difference, right? We apply a log rank test, which is chi-square distributed with 1 degree of freedom, and this is your p-value, which is significant. So this tells me there is a significant difference. How you want to report your result? That's very important. Here it is. So we use a log rank test, right, to see the significant difference between the survival distribution of the control group and the treatment group. The median of the control group is 8. The median of the treatment group is 23. Remember, you have to report the median, not the median. And you can see there's a difference. And the p-value is your scientific evidence, which is less than 0.05. So we can say there is a sufficient evidence to reject the null hypothesis, the equality of the two survival distribution, and conclude the survival time of treatment group is higher than the control group in the population at 5% level of significant, right? So that's your, you, this is the way you can report your results, and you want to tell the, like a layman or those who don't know much about statistics, you can, okay, there are some limitation, advantages, assumption. So the first assumption is your uh, status should be either censored or event, right? Right, and the time is like precisely, you have to define your time precisely in weeks, months, day, and so on. Okay, censoring an event independent. Remember, we told already, like uh, event, if your event is death, if the death happen with some other reason, it is censoring. It means censoring because this is nothing related to this one. So censoring and events are independent. Okay, and there is this another assumption: the pattern of censorship in both group is same, but unfortunately, in our previous example, they are not. The pattern was not similar. Remember, so that's one of assumption. So that could be the limitation of that analysis. Advantages: very robust, fairly robust. Mean you can use any for any data. Efficient, relevant to parametric method. What does it mean? It means you need small sample, not a big sample. In parametric, you need a large sample. So to, for the efficiency, small sample. If, for example, efficiency, I could say the work, if 10, for example, if 10 sample of size 10 give you the same information, and if the sample of size 6 gives you the same information, so 6, the method you use with the 6 number is more efficient because you need uh, smaller number as compared to others, so less resources, less work, right? So the Kaplan-Meier is more efficient. Simple and intuitive. Yes, we can see very simple to understand. Limitation: Kaplan-Meier only is used for single right sensor data. See, I told you. We know there are lots of other data like truncation, left censored, interval sensor, right censoring, random censoring. So the Kaplan-Meier is only for the right censoring. Only on incorporate with one categorical variable at a time, right? See, we only use one variable at a time. If you want to use more than two categorical variables, you need more graph or more information, right? And for the multivariable analysis, it's not like efficient. We cannot use this Kaplan-Meier at a time. Also, it's a non-parametric method. Therefore, no simpler way form our summarization relationship between the response and the predicted variable. Like how? Remember in regression or logistic regression, we have an equation and we have a relationship that we can summarize by the equation. But in Kaplan-Meier, we don't have such kind of information. What else we have? Another other non-parametric Nelson-Allen method. You can see this, but I don't want to discuss this because it's not very important. But sometimes people use this one when you have a small sample. It's very informative. You can use this Nelson-Allen estimator. Uh, Asymptotically, for the large sample, it will be equivalent to Kaplan-Meier estimator. We have another method which is life table. So main focus is on Kaplan-Meier estimation method. Hope you will learn this Kaplan-Meier method. If you have any question, let me know. And next time we will talk about semi-parametric method. And thank you very much for watching, and bye bye from now.